Hey, Physics 30s, how's it going? So today we are going to continue on. We're going to talk about the photoelectric effect. The crash course video has already talked about what the photoelectric effect sort of is and how it kind of helps prove this idea that light behaves as a particle and not as a wave. We'll talk a little bit more in depth as well. There are two other videos I want you to look at as well, if you haven't done so already. There's one at the top of this page here, right over there. Right there. Also, the two links in the Google Classroom there. One is the demonstration of the photoelectric effect. It's actually pretty good quality for that one. And one is just kind of an animation about the history of the photoelectric effect. If you want to go back and refresh, go look back at that crash course video in the previous one. In the second half, they talk about the photoelectric effect. And there's some key things in there which we're going to talk about intensity. What does intensity mean? What's the energy of frequency? How do they relate to each other? And then of this electron that's been ejected out. So Einstein, this is where Einstein got his Nobel Prize for. He studied the effects of light as it shone on top of a metal, and then how these electrons are then ejected out. They found, Millikan and a few other people have found, that if you shine light on a metal surface, electrons are eventually, or emitted, not eventually, but emitted from the metals in an immediate fashion, not a buildup over time. Like one of the classical physics idea of this is if I just shine a red light on a metal, the amount of energy that the electrons build up over time will eventually just eject them out. But they realized that if I just shine a red light on a metal and that red light doesn't have enough energy, no matter how long I leave it on there, it's just going to stay. The electrons are going to stay within the metal. They're not going to be absorbed, or not going to absorb those photons. They're not going to be ejected out. But they realized that if you change the frequency of the light, which means changing the energy of the light, eventually what's going to happen is that photons will then start being ejected out. If I hit the right frequency and go beyond that frequency, and that frequency we call the threshold frequency of that metal. So shine light with a very specific frequency or higher, and the electrons are ejected out. Now, as I slowly increase my frequency, the electron speed that's being ejected out increases as well, because only a certain amount of the photon energy is actually used to dig an electron out of the metal. What's left over, the electron just takes and uses it as kinetic energy, so it goes a little bit faster. Okay? So that's the idea of a photoelectric effect. Metal hits a surface, light hits a surface. The light is absorbed by the electrons, and the electrons pop out. Now, this is a 1-for-1 ratio, right? Which means one photon for every electron. Not two photons for every electron, not half a photon for an electron, right? It's a 1-to-1 ratio. So if you detect 5 electrons, that means 5 photons were used to get those electrons out. That's it. Right? It doesn't mean that I could shoot like millions and millions of photons out there at the surface. But if you only detect 5 electrons, only 5 of those million photons were actually used to get the electrons out. The other photons, maybe they were absorbed by electrons that are deeper in. So you can see this little picture here, like maybe this one down here, these are all just little packets of very specific amounts of energy. Maybe this guy's too deep in. So if he gets a photon absorbed here, maybe that's not enough energy to get him out. Right? If it's not enough energy to get him out, he's not going to use him. So that photon will just reflect back and not be used at all. So it's not like, oh, I'll use a little bit, move up, and then I'll use a little bit more and move up, and then I'll use a little bit more and move up, and then I'm out. If it's not enough to get me out completely, he's not going to use it at all. All right, so there's no buildup. So it's not going to be like 5 photons can get me out. It has to be 1 photon and 1 photon only. If it's not enough, then it doesn't work. So that's the idea of this photoelectric effect. Right? There's going to be some questions later on where we talk about, oh, here's the current. Remember, current is coulombs per second. Here's the current that's being produced. How many photons are required to produce that current? Well, you'd have to find the number of electrons, and then the number of electrons corresponds to the photons because it's the 1-to-1 ratio, and then Now you know how many photons there are. Okay? And we could do that because we know what current is. It's coulombs per second, et cetera, et cetera. Okay. So we are going to talk about the properties. I'm just going to highlight a few of these properties of the photoelectric effect here. Some of the things that they observed and saw as they did these experiments here. Okay, so what they noticed that electrons were emitted immediately when the light hit the surface. It wasn't over time or anything. It didn't take like a couple seconds for it to build up and then start ejecting electrons. It was an immediate thing. All right, so electron absorbed a photon and it immediately popped out and off it went. There was no time limit. There's no buildup of energy. It took all the energy, if it could, and off went off with it. There's a threshold frequency, right? There's a threshold frequency. So that just means that if I don't hit this threshold frequency, if my photons don't have enough energy, then there's no photo emission. So I'm going to say a couple of words like there's a photoelectron, which is just an electron that's emitted by the photoelectric effect. So those are the same thing. A photo emission is also the same thing as a photoelectron and just an electron. Yeah. So when I talk about the photoelectric effect, we're always talking about electrons. And there's just three different ways of representing it. You could just say electron, you could say photoelectron, or you could say photo emission. And they all just kind of mean the same thing. So I'm just going to maybe write that down here in the notes. So we have that. So an electron is the same as a photoelectron, which is the same as a photo emission. So these, oh, that's, yeah. I mean, M's are an emission. Okay. So these all mean the same thing when it comes to these kind of examples. Okay. So so this idea of one-to-one photon is very important for the second one, because if it wasn't one-for-one photon, what if I can just keep on stacking enough photon energy into those electrons, and electrons eventually dig this up? So imagine the top of this box here is the top of the metal, and we're inside the metal here. There's an electron down here. Here's my electron. Okay. Now, if a photon comes in, pops and hits them, it has to have enough energy to get them right to the very top and then out, right? Now, it has to be one for one. That's why it's an immediate thing. So it's not a buildup. So it's not like hit them, then moves up just a little bit, and then another one comes and hits them, and then another one comes and hits them, and then another one comes and hits them, and then eventually pops out. No, that didn't happen. Right? That wasn't one of the observations they saw. And they also saw this. What if it wasn't enough energy at all? Like, say this is just red light. Remember, lower frequencies, lower energies. If I just shine red light on this metal, eventually those electrons would pop out, according to classical old physics. Right? But now, if I shine red light on this, the red light would hit the electron. The electron would be like, no, I don't want this. And then the red light just reflects off and goes away. Right? So the electron's not going to use it. It's not even going to absorb it. It's just knows that it's not going to be able to need it to get out, so it doesn't use it at all. If it was a little bit closer, maybe the red light could get them out, right? In one step, but it has to be one photon to get them out. Okay? But all metals have a different threshold frequency too. So even the ones at the very top of the metal there, red light may not be enough to get them out. Maybe it has to be a green light to pop them out, just enough to get them out. So there's a threshold to all these metals. And the lab that you'll do tomorrow, we'll talk about those threshold frequencies. Okay. Yeah, so we got that. It's a one-to-one. It's in here somewhere. Yeah, right down here. It's only one and one photon has to be used to do this. Okay. So we got electrons, photo emissions. Those all mean the same thing. Let's go down here. Every metal has its own characteristic threshold frequency. You can see this little diagram over there. That this is data from Millikan from a while ago. They talk about the maximum photoelectron kinetic energy. We'll talk about how to calculate that in a bit. And then the bottom is the frequency. You notice that once you hit a certain frequency, so right here, that's the threshold frequency. Anything below that, there's no electron kinetic energy. That means there's no electron coming out, right? There's no movement in those electrons. Once you hit that, then there's all of a sudden there's this kinetic energy of the electron. And you notice that's also a nice constant amount as well. Right? It's not going to exponentially increase or anything. And the reason behind that is because the energy required to get the electron out is a constant number. So all these electrons, they're all coming out. They use the same amount of energy to get out, but the energy of the photons have increased a little bit. So the one that absorbed the red light, it got out. Maybe it's like orange light or something. It got out, but didn't have that much energy left over. But then one that absorbed the blue light, it got out. Took the same amount of energy to get out, but now has more energy to move faster. And violet light, ultraviolet, et cetera, as you go down the frequency here, you can see, or go up the frequency. Okay, so there's a little crossing point here, right at the x-intercept. Very key, probably very important for the virtual lab that you're going to do tomorrow, or whenever you do it. Is the x-intercept is very important. You need to be able to see the x-intercept on your graph, so you have to change your graph around. Then you just read the x-intercept off the graph, and that's your threshold frequency. Okay. That threshold frequency could also be changed into energy as well. So you can determine like the threshold energy. We call that the work function. That's later on here. I'll talk about that in a bit. Okay. This is more about if light is above that threshold frequency, then electrons are emitted. Now, intensity is a little bit different here. This FET thing doesn't work anymore because it's Java. If the intensity increases, the electrons don't increase in size. That was mentioned in one of the videos as well. Or the electrons don't increase in speed, I shouldn't say, not in size, but in speed. Is in one of the videos she talked about. Intensity means the number of photons, not the energy of the photons. It just means that I have more photons. But remember, it's a one-to-one thing, so it's not like all these photons are going to be used on less electrons. It just means I'm going to be ejecting more electrons per second. But all those electrons per second will have the same amount of energy they had before with the lower intensity. So it's not going to change how fast they're going to be going out when they come out. They'll just change how many there are. That's a very important thing. Intensity is how many photons there are, which will increase the current. We'll talk about that. Remember, current's electrons per second. So if I have more electrons being emitted, I have more electrons per second. I have more current. That doesn't mean they're going faster. It just means I have more of them. Okay. This couldn't be explained by classical physics. I was talking about this already. The wave model states that over time, the energy should just be absorbed by the electron and it should be eventually just dig itself out and pop out. Off it goes. But it doesn't. It stays where it is, no matter how long you put those low frequency lights on there. And one of the classical ones says if I just increase the intensity, more and more waves, because waves superimpose each other. So these intensities, the wave amplitudes get bigger and bigger. I should be able to force them out faster. It doesn't work as well, right? If I have high intensity but low frequency, nothing happens. As long as if I'm below the threshold frequency. Intensity just talks about the number of photons. If the photons don't have enough energy to get the electron out, it's not going to be used. This just talks about the same thing. They're not transferred continuously. They suggest that they're transferred in bundles. So very key here. I'm just going to highlight. It's in bold already. But one photon for every one electron. Very key. Right? We'll go through a couple of examples when we use that information as well. If it doesn't have enough energy, it stays in the metal, explains special frequency, blah, blah, blah. Okay. I'm running to the end of this video here. So I want to just talk about, this last slide here. So even though photons that have enough energy can cause photon emissions, not all of those electrons will have the same exit velocity because some will be closer to the surface, some will be a little bit more deeper, so they'll use it just a little bit more to get out. But if they're all right around the surface here, they'll all use about the same energy to get out. The ones that are deeper might use a little bit more energy to get out. The ones that are even deeper might use more energy to get out as well, right? So they don't always have to have the same exit velocities, when you look at the lab or look at any demonstration, they always talk about what's the maximum. The maximum would be the ones right at the top there. That's the threshold, right? So if I'm just sitting right at the top and a photon comes and hits me, that is the threshold frequency, the energy required to get me out, right at the very, very top. Down here, this guy may not be able to get him out, right? Because he has too much to go, but higher frequencies, higher energy might be able to get him out. Yeah. Now you can read through this one as well. And the intensity of light is just the number of electrons, affects the number of electrons. It does not increase the speed. I'm going to mention that. So it affects the number of electrons, increases current, but not the speed / kinetic energy. I don't know what's going on there. Of the electrons. Not. Okay. And I'll see you in the next video, the second part.